Isn't it a strange situation we're in with physics? We have the standard model, this incredibly successful framework, explains most forces, particles, but then gravity, it just feels completely separate, right? Einstein's theory over here, everything else over there.
Uh-huh. It's like having this amazing recipe book, but yeah, the instructions for the main course are just missing.
Exactly. And you start to wonder, couldn't there be, I don't know, a deeper, more unified recipe underneath it all?
Well, that feeling, that sense of a missing ingredient, maybe a deeper unity, that's exactly what drives people to explore theories like geometric unity or GU, Eric Weinstein's proposal.
Right.
And the ambition here is, well, it's immense. Trying to describe all the fundamental forces, all the particles, just using the language of geometry. It's elegant, if it works.
Now, for you joining us, this might sound like diving straight into the deep end of the theoretical physics pool. It's definitely a complex landscape, and you might hit ideas that feel, well, pretty unfamiliar.
Sure.
But that's exactly why we're doing this deep dive. Our mission, really, is to pull out the core insights, those surprising connections, the big shifts in thinking, without getting totally bogged down in equations.
Yeah, avoid the jargon swamp if we can.
We've got some fantastic material to help, including a really detailed explanation by Kurt J. Mangal on YouTube. That's been super helpful.
Think of it like this. We're highlighting the most fascinating landmarks on this really complex map. Our goal is just to give you a clear, maybe high-level, but still useful understanding of what geometric unity is actually about.
What are the core principles? How does it try to solve these huge, long-standing problems in physics? What are the implications?
Exactly. We're trying to distill the essence of this very ambitious framework for you.
And yeah, our main guide for this whole expedition is that in-depth video explanation. It really gets into the weeds. So, okay, with a topic this huge, where do we even begin to unravel it?
I think a natural starting point is to look at what geometric unity is trying to build on.
Yeah.
And, in some ways, what it's trying to move beyond.
Okay.
So think about our current understanding, right? The standard model of particle physics. Let's just see that as the very, very tip of a huge iceberg.
Okay, the iceberg tip. So let's explore underneath the surface then. What's down there that the standard model doesn't quite get, or where does it feel, incomplete?
Well, the standard model is amazing, no question. It details the strong, weak, and electromagnetic forces beautifully. Mathematically, it uses this thing called a gauge group. It's kind of symmetry structure. You might have heard it SU3, SU2, XU1.
Classic trio.
And it's got the Higgs mechanism, explaining how particles get mass. It describes the three generations of matter, like electrons, muons, tachys, the quarks.
Those repeating families, yeah.
And how they mix, governed by things like the CKM and PM&S matrices. And then, completely separately, we have Einstein's field equations for gravity and the Yang-Mills equations for those other forces.
Okay, so two totally separate rule books for different bits of reality. Where's the fundamental disconnect, the tension?
The core tension, and Eric Weinstein really hammers this point, is what he calls the twin origins problem.
The origins.
Gravity, right.
Yeah.
Described by the metric tensor in general relativity. That basically tells us about distances and curvature in space-time.
Space-time bends, yeah.
And then the other forces described by gauge potentials in Yang-Mills theory. That's about how forces are mediated, how particles interact. These two things, the metric and the gauge potentials, they just have fundamentally different mathematical structures.
Different kinds of math objects.
Exactly. And crucially, they behave differently under symmetries. I mean, you can draw some analogies like both involve ideas of curvature in a way. But when you look at how the equations stay the same under different perspectives, like gauge covariance in Yang-Mills.
Right, that's key for forces.
Gravity, as we usually write it down, doesn't naturally play nicely with those gauge symmetries. It's like trying to fit a square peg in a round hole, mathematically speaking.
Okay, so different languages, different rules. How does geometric unity even try to bridge that gap, bring them together?
Well, the foundation of DU involves a really interesting kind of radical shift in perspective. Instead of starting with our usual four-dimensional space-time, let's call it x4, with a fixed way of measuring distance, a specific metric.
Like we normally do in physics.
Right. GU starts with that x4, but then it builds this much, much larger space. It's 14-dimensional, called the obserververse, or Y14.
14 dimensions, whoa.
Yeah, and the idea is imagine that at every single point in our normal 4D spacetime, this Y14 space holds all possible ways you could define distances and curvature at that point, all possible metrics.
All possible geometries at every point. That sounds incredibly abstract. Why start there? What's the point?
It sounds abstract, But it's crucial because it directly attacks this fundamental puzzle in quantum gravity. It's a kind of chicken-egg problem. Like, how can you even define fundamental particles like fermions, electrons, quarks, which mathematically need a geometry to exist, if at the quantum level, the geometry itself might be fluctuating like crazy, or maybe not even well-defined?
Ah, right. If space-time itself is fuzzy, how do you define things that live in it?
Exactly. So by considering all possible geometries at once, GU avoids having to pick one specific, possibly ill-defined geometry right at the start.
Okay, I think I see the motivation. It sidesteps that initial choice. So we're in this 14-dimensional obserververse with all possible geometries. How do we get back to describing the particles and forces we actually, see?
Right, good question. This is where another key idea comes in,
Hmm.
the chimaic bundle over this Y14 space.
Chimaic bundle.
Think of a bundle as just like attaching some extra mathematical structure to each point in our space.
Yeah.
This chimaic bundle, it combines two kinds of structures, one related to how the geometry itself can change at a point, and one related to how we move through the underlying spacetime. Now, what's really interesting is that part of this bundle naturally has a way to measure distances within itself. It uses something called a Frobenius inner product.
A built-in ruler for part of this extra structure?
Sort of, yeah. And that allows us to define spinors, the mathematical things that describe fermions, particles with spin within this 14D space, without needing to have already picked a specific geometry for our normal 4D spacetime.
Whoa, okay. So you can define the math for matter particles before you've settled on the exact shape of space-time.
That's the idea. It's like defining the ingredients before you finalize the recipe. It looks like a big step towards solving that chicken and egg problem.
Makes sense. What about the forces, then? How do they fit in?
For forces, Weinstein introduces this concept of the inhomogeneous gauge group. Now, think about regular space-time symmetries, the Poincare group, that includes rotations, boosts, but also translations, moving around.
Right, shifting position.
The inhomogeneous gauge group in GU is kind of analogous. It combines the usual gauge transformations, the symmetries underlying forces like electromagnetism, with something like translations. But these are translations in the more abstract space of connection.
Connections, those things that tell fields how to change from point to point. So translations in the space of those.
Exactly. It's a bit abstract, but you can see the parallel to Poincaré's translations in spacetime.
Okay, I think I follow the analogy. How does this help unify gravity with the other forces, though?
This is where the augmented torsion tensor comes in. It's a really crucial piece.
Augmented torsion. Okay.
In geometry, torsion is basically a measure of twisting, or how parallel lines might fail to stay parallel. The augmented torsion tensor in GU is this carefully built mathematical object. It includes aspects of this geometric torsion, but critically, it's designed to behave consistently with those gauge transformations for the other forces.
So it speaks both languages, geometry and gauge theory.
That's a great way to put it. It's the key to bridging that twin origins problem. It lets you describe gravity and the other forces within one common mathematical language that respects both geometric symmetries and gauge symmetries. It acts like a translator.
Okay, so this augmented torsion thing helps bridge the gap. But where does the specific set of forces we see, the standard models SU3, SU2, XU1 group, actually come from? It always felt a bit arbitrary, just tacked on in the standard model.
Right. Why those groups? Well, instead of just postulating them, GU proposes that this specific structure emerges naturally from a larger underlying mathematical structure.
Oh.
Weinstein uses a larger group, one that's non-compact, and the SU3, SU2, XU1 structure pops out as its maximal compact subgroup.
So it's not just three random choices, it's a consequence of the deeper geometry breaking down in a specific way.
Precisely. It's seen as a result of the underlying symmetries, not just an input assumption.
That's a much more compelling picture. What about the different types of matter particles, the three generations, electron, muon, tau? Y3, the standard model just lists them.
Yeah, why the triplication? GU proposes that this also arises naturally from the mathematics in that higher Y14 space. It's about how certain spinor-valued mathematical objects decompose.
Decompose, like breaking down.
Sort of. There's a specific structure called a zero form, related to spinors, and that accounts for the first two generations. Then another related object, a Rorita-Schwinger field, accounts for the third. And this all comes from just the basic assumptions about the initial 4D spacetime, X4. It's not arbitrary. It's supposedly woven into the math.
So the big idea in GU isn't just adding new bits to our existing theories. It's more like realizing that all the familiar ingredients, gravity, the forces, the particles, maybe even the Higgs, were already hidden inside the geometry of this obserververse, built on top of our regular space-time.
Exactly. That's the core claim. The fundamental pieces were there all along. We just needed this broader geometric perspective to see them unified.
Okay, let's get a bit more precise about this obserververse then. You said it's like a triple X4, Y14.
Right. X4 is our base 4D spacetime. Y14 is that huge space containing all possible metrics at each point of X4. And pi is the projection, the map connecting Y14 back down to X4. GU works with all these possible metrics simultaneously living in Y14.
Still wrapping my head around working with all metrics at once. How do we get back down to our everyday experience of just one space-time geometry? Seems pretty fixed, usually.
Good point. This is where pullback maps and observation maps come in. Think of an observation map as like taking a local snapshot. It's a smooth way of picking out one specific geometry from that huge space of possibilities at each point in X4.
Like choosing a specific lens to look through.
That's a great analogy. And then pullback maps. Let us take the mathematical information defined up on the big Y14 space and bring it back down to our familiar X4 spacetime. Using those chosen snapshots or lenses, they're like probes, letting us extract specific data from the space of all possible metrics.
Okay, probes and lenses. Got it. And you mentioned something about spin 1-3 arising naturally. That's related to space-time symmetries, right?
Yes, bin 1-3 is crucial. It's the group related to Lorentz transformations, boosts, and rotations in space-time. The standard geometric setup doesn't automatically allow for spinors, those things we need for fermions. Spin 1-3 is a sort of double cover of the Lorentz group, and it does have the right structure to incorporate spinors. GU argues this spin 1 structure arises naturally from the geometry within Y14.
Double covers, spinors. Yeah, it gets abstract fast. So what are the essential math tools we need inside this 14D obserververse, Y14?
Well, we need to think about the tangent bundle of Y14. It's
Yeah.
like all the possible directions you can move in Y14. And it's dual, the cotangent bundle. Different kinds of fields naturally live in one or the other.
Okay, directions and their duals.
And interestingly, unless you've already defined a metric, a way to measure distances on Y14 itself, these two bundles aren't automatically equivalent.
Right, and those vertical and horizontal bundles you mentioned earlier, where do they fit?
Yeah, so at each point in Y14, you can split the tangent space, the directions you can go, into two parts. A vertical part that corresponds to changing the metric itself at that point in X4, and horizontal part, which relates to moving around within the base X4 spacetime. Making this split requires choosing a connection.
Ah, the connection choice again.
Yeah.
And the Frobenius inner product came back with the vertical part.
Exactly. That Frobenius thing gives us a natural way to measure size or distance, specifically within that vertical direction, the space of changing metrics, which is really important mathematically.
Okay.
Now, when we think about spinors in this whole setup, there's a key property called the exponential property of spinors that basically tells us how spinning particles behave when you combine different spaces with their own metrics. And when we use those observation maps, our lenses, to bring the spinor description from the chemic bundle on Y14 back down to our familiar X4 spacetime, this property leads to this really neat separation. You get the properties we associate with spacetime, like spin and how particles react to boosts and rotations, and you also get the internal quantum numbers.
Wait, so things like color charge for quarks or weak isospin?
Yep.
Those seemingly random internal labels aren't just added by hand. They actually emerge from the geometry of this higher dimensional space when we look at it through our 4D lens.
That is precisely the claim of geometric unity. And crucially, this whole mathematical machine lets us define spinors without needing a metric on spacetime first. It directly tackles that chicken and egg problem.
That really seems like a potential breakthrough. Okay, how does that spin 7 group fit into all this? You mentioned it earlier.
Oh yes, spin 7-7. That structure group and its representations are absolutely fundamental. Remember the Frobenius inner product giving a metric on the vertical bundle? That has a mathematical signature we write as 4.6, 4 pluses, 6 minuses, essentially. Combine that with the 1-3 signature of our regular spacetime, 1 time 3 space dimensions. Add them up, sort of. 4 plus 1, 6 plus 3 gives 5, 9, or sometimes thought of as 7-7, depending on the exact construction details related to real versus complex numbers. The point is, you get this larger spin group signature.
7-7, got it.
And the mathematical objects that transform under the spin 7 group, the spinors, are quite complex. They turn out to be 128-dimensional, breaking into two 64-dimensional chunks. And that number 64 Well, it turns out to be deeply connected to the complexity we see in the standard model families.
It's G4, leading to that U64064 gauge group you mentioned. That sounded very technical.
It is technical, yeah, but the core idea is those 128-dimensional spin-7 spinors preserve a certain mathematical structure, like a metric with a 64 pluses and 64 minuses signature. Because of that, we can build this framework called a principal bundle, where the symmetries are described by this unitary group, U64064. It's a more robust way to handle the gauge theory aspects than just using spin-7 directly.
Okay, so U64064 is the symmetry group acting on these complex spinors. And we're back to the inhomogeneous gauge group again.
Exactly. Think of U64064 as the group of internal symmetries acting on those spinors. The inhomogeneous gauge group then combines these internal transformations with those translations in the space of connections we talked about.
Like Poincaré combines spacetime symmetries and translations.
Precisely the analogy, and it involves understanding exactly how this combined group acts on the connections themselves, which, yeah, it's not trivial. There's a specific mathematical formula for the right action on connections.
And that's how this combined gauge group actually interacts with the force fields, the connections.
Yes, that formula is built to ensure mathematical consistency, to make the space of connections behave properly under this larger symmetry group.
Okay, deep breath. So all this complex math, the observer-verse, bundles, U64064, inhomogeneous groups, it's all building towards fixing that twin origins problem using the augmented torsion tensor.
Yes, that augmented torsion tensor involving the gauge potential, that variational pi representing force fields and how things change under gauge transformations, that's the crucial link. It's designed to transform correctly under both gauge transformations and changes in spacetime coordinates. Diffeomorphisms. It bridges the gap.
Got it. And finally, the Chiab operator, where does that fit in this unification picture?
The Chiab operator is GU's way of generalizing a really fundamental operation in Einstein's gravity. In GR, you take the Riemann curvature tensor, which measures spacetime curvature, and you contract it to get the Ricci tensor, which appears in Einstein's equations.
Right, a standard step.
But the standard way of doing that contraction doesn't respect gauge covariance. The Chiab operator does. It takes certain mathematical objects, gauge covariant 2 forms, and produces other related objects that also transform nicely under gauge transformations. It essentially bakes the gauge symmetry into the contraction process itself.
So it's a way to extract curvature information that's compatible with the rules governing the other forces.
Precisely. It's a custom-built mathematical tool that respects the gauge structure while doing something analogous to the contraction that gives us the Einstein tensor in GR.
Wow, okay. We've built this incredibly elaborate mathematical foundation. Now, how does geometric unity actually go about deriving the familiar equations, the ones that govern the universe we actually observe?
Right, the payoff. The fundamental principle in GU, the action principle, the thing you start with to get the equations of motion, is really remarkable. Its mathematical form actually looks a bit like both the Einstein-Hilbert action from GR and a type of theory called Chern-Simons theory.
Interesting mix.
What's really notable is that it only involves first derivatives of the field.
Only first derivatives. For gravity, that's different from standard GR, which uses second derivatives.
It is, and that's a key feature, linking it more closely to the math of gauge theories. This action involves the augmented torsion and the curvature processed through that Chiab operator. There's even a term that looks like a mass for the torsion field.
Okay. And the field equations come from varying this action.
Yep, the usual process. And the resulting equations involve the Chiab operator acting on curvature, plus terms with the augmented torsion. It describes how the geometric fields evolve.
What about matter? The fermions, how do they get into the action and equations?
In GU, fermions are conceptually tied to being like square roots of the gauge potentials. Mathematically, we use objects called spinor-valued forms. These lead to an operator that's analogous to the Dirac operator, the one describing fermions in quantum field theory.
Okay, so a Dirac-like equation emerges.
Yes, and interestingly, the framework hints at a different kind of supersymmetry. Not the usual spacetime kind, but one based on symmetries in that abstract space of connections.
Supersymmetry based on connections. That's wild.
And when you mathematically break down the spinor representations under that spin-7-7 group, you find exactly the right structure to fit the 3 generations of fermions we see in nature.
So the 3 families fall out naturally again. What about understanding fluctuations? Like, how stable are solutions in GU, and what are the real physical ripples?
To study those small changes, GU uses a mathematical tool called a deformation complex. It helps figure out the true physical degrees of freedom. Its cohomology, a way of finding the essential, non-redundant structures, tells you about the physically distinct ways you can wiggle a solution. It's analogous to how different vector potentials can give the same E&M fields.
Makes sense. And what about those really tricky puzzles, like why neutrinos have tiny masses or why the generations have such different masses? Any clues from GU?
Well, yes, there's a structure within GU called the Dirac-Rarita-Schwinger complex. Mathematically, it looks quite similar to the seesaw mechanism, often used to explain small neutrino masses.
The seesaw, right. Heavy partners making the known ones light.
Exactly. In GU, a similar kind of mathematical mixing happens between different spinor components. This could potentially provide a framework not just for neutrino masses, but maybe even for understanding the whole hierarchy of fermion masses across the three generations.
That would be huge. Now, we keep mentioning spin 77 and how it relates to the standard model group. Can you walk us through that connection again, maybe a bit more detail?
Sure. The process involves starting with spin 7, related, slightly different, and mathematically reducing it down to the standard model's SU2, XU1. It's not a direct jump, though. It goes through a sequence of intermediate subgroups.
Steps along the way.
Right. And crucially, it involves using certain non-compact groups, like SU32, in the middle. This specific pathway is important because it might help GU avoid problems that older grand unified theories, GUTs, had, like predicting protons should decay way too fast.
Avoiding those proton decay issues. That was a big hurdle for old GUTs.
Exactly. So by carefully choosing the sequence of symmetry breaking, the standard model gauge group emerges at the end, hopefully without the unwanted side effects.
So again, the forces in their structure aren't just put in, they're a result of this larger geometric symmetry breaking down.
That's the central idea. And the three generations themselves, as we touched on, come from that Dirac-Rarita-Schwinger complex on Y14. One piece gives the first generation, another piece breaks down further for the second and third, and each generation's worth of fields mathematically fits into a 16-dimensional representation exactly matching the count of fundamental fermions per family in the standard model.
16 dimensions per family. That match is striking. Okay, what about the Higgs? The particle that gives mass. Where does that fit into this purely geometric picture? It feels so tacked on in the standard model sometimes.
Right. In GU, the proposal is that the Higgs field is actually part of the gauge potential itself. Remember that variational pi?
The thing representing the force fields, yeah.
When you take that gauge potential, living up in Y14, and use the pullback maps to bring it down to our 4D spacetime, X4, it decomposes. It breaks into different mathematical pieces. One of those pieces behaves exactly like the Higgs field.
Part of the force field becomes the Higgs.
It comes from the decomposition of symmetric 2 tensors. These have a trace part and a traceless part. The traceless part is identified with the graviton spin 2, mediating gravity.
Yeah.
And the trace part, that's identified with the Higgs boson spin 0.
Wait. The Higgs and the graviton, seemingly totally different things, are actually just different mathematical aspects of the same underlying geometric object in GU.
That's the claim. It's a really powerful unifying idea if it holds up.
Wow. That's a different way of looking at things.
And it gets better. The way forces interact in GU, described by terms similar to the Yang-Mills action, naturally produces the right kind of energy potential for this Higgs-like component. You get the characteristic quartic potential, the Mexican hat shape.
The Mexican hat potential just falls out, the thing that's crucial for symmetry breaking and giving mass.
It emerges naturally from the gauge theory structure when you include this Higgs-like component derived from the gauge potential itself.
Okay, mind slightly blown. What about Yukawa couplings? Those numbers in the standard model that tell us how strongly each fermion couples to the Higgs, determining their specific mass. They always seemed completely arbitrary.
Yeah, just a list of numbers we measure. In GU, the Yukawa coupling isn't an extra input. It arises naturally as a form of minimal coupling within the Dirac operator, the thing describing fermions.
Minimal coupling, like how charge couples to the electromagnetic field.
Exactly like that. When the Dirac operator interacts with the gauge potential, which, remember, contains the Higgs component, the resulting interaction term automatically has the mathematical form of the Yukawa coupling.
So it's not an ad hoc addition, it's just how fermions naturally interact with this combined gauge-Higgs field in the GU framework.
That's the idea. It's a direct consequence of the geometry and the structure of the operators.
This means the Higgs sector and the Yang-Mills force sector, which look pretty distinct in the standard model, are actually deeply intrinsically tangled up in geometric unity.
Yes, there's a really remarkable correspondence. The terms describing the Higgs's motion, its kinetic terms, and its self-interaction, the quartic potential, they all arise from decomposing the gauge potential. And they mathematically match what we expect from standard Higgs-Yukawa theory.
Incredible. And that earlier issue about needing a quadratic term in Einstein's equations to make them gauge covariant, does GU handle that?
It does. Geometric unity inherently includes a term in its gravity formulation that's quadratic in curvature, much like the self-interaction terms in Yang-Mills theory. This is essential to ensure the gravity equations are consistent under gauge transformations, just like the equations for the other forces.
Okay. Even things like the cosmological constant, the energy of empty space, or the CKM matrix describing quark mixing, do they come from somewhere in GU?
The claim is yes. Different mathematical components of that gauge potential, that variational pi, when pulled back down to x4, are suggested to contribute to the cosmological constant term in the effective Einstein equations, and also to determine the mixing angles between quark generations, the CKM matrix parameters. Things we usually treat as fundamental constants or inputs might be derivable outputs in GU.
It's just astounding how many disparate pieces of the standard model in GR seem to potentially emerge from this single geometric framework. What about the fundamental equations themselves? Dirac, Klein-Gordon, Yang-Mills, Higgs?
GU aims to derive all of them from its geometric foundations. The GU version of the Einstein-Hilbert action uses the curvature of a special connection on a mathematically lifted version of the frame bundle. Getting the Einstein tensor involves reinterpreting the contraction using an algebraic operator on the metric bundle Y14, then pulling back to X4. Similarly, the Yang-Mills-Maxwell equations for forces, the Dirac equation for fermions, the Klein-Gordon for scalars like the Higgs, they all have proposed derivations within GU, relying on the chimaic bundle, the Schaub operator, the decomposition of the gauge potential, and so on.
So at its heart, GU paints this picture of reality that's incredibly elegant and deeply interconnected, even if the math to show it is formidable.
Exactly. And despite all the apparent complexity we've discussed, proponents argue there's an underlying simplicity to the fundamental equations within GU.
How so?
Well, the Dirac equation has deep links to K-theory in mathematics. Yang-Mills can be seen as the simplest geometric equation involving curvature. Einstein's equations come from the simplest Lagrangian scalar curvature. Even the Klein-Gordon equation seems to have a natural geometric home here.
And that idea of the Higgs just being a vertical component of a connection form, that's just a totally novel way to think about it, isn't it?
It really is. And Weinstein's whole approach of lifting the frame bundle, dealing with spinors via this obserververse, it tries to make the description of matter more fundamentally topological, less dependent on the fine details of a specific space-time metric at the outset.
Okay, so if I were to try and summarize the overall flow, the logic,
Yeah.
is it start with a basic 4D space-time manifold, build this huge 14D space of all possible metrics on top of it, use these observation maps or sections to connect back down, and then somehow the standard model and gravity just emerge from the geometry of that higher space?
That's a remarkably concise and accurate summary of the grand ambition, yes.
Okay.
Think of it maybe like this. The standard model, with all its different particles and forces, it feels like a jigsaw puzzle someone smashed, right?
Yeah.
Lots of pieces that fit together nicely in groups, but the overall picture isn't clear.
Yeah, fragmented.
And gravity, Einstein's theory, it feels like this beautiful, pristine, complete disk, but totally separate from the puzzle pieces. Geometric unity is the framework that suggests if you look closer at that pristine disk of gravity from the right perspective, this higher dimensional geometric view, you realize it actually contains all the jigsaw pieces of the standard model already embedded within its structure. They weren't separate after all.
The fragmented image fits inside the complete picture. I really like that analogy. What about that TI one? I think I heard that somewhere.
Yeah, the Kion analogy. Imagine our familiar 4D spacetime is like a single blade of grass, a kiite.
Okay, one blade.
And growing out from this blade are countless tiny, almost invisible fibers. Those fibers represent all the different fundamental particles and forces. It's a visual metaphor for how this rich world of stuff might emerge from a more fundamental geometric base, the blade of grass.
The particles as fibers growing off space-time. Interesting visual. And just to circle back, this whole complex structure, the obserververse, it fundamentally aims to solve that chicken and egg problem, right? How to define matter, the spinors, when the underlying geometry might be quantum and fuzzy.
That's arguably one of its primary motivations, yes. Defining matter before you fix the metric.
Okay. Now, if someone listening is, say, a graduate student in physics, just trying to get a handle on GU, what are the absolute must-know key concepts they should focus on first?
Right, the essentials, I'd
Yeah.
say. Grasp the construction of the metric bundle, the obserververse, Y14. Understand the importance of choosing a connection, often called the Zorro connection. Get familiar with the definition and role of the chemaic bundle. Know what the augmented torsion tensor and the Shiab operator do. Understand the Dirac-Rita-Schwinger complex for fermions. And finally, see how the standard model components gauge groups, particles, are supposed to emerge via reduction and decomposition.
Okay, that's a solid list. And for someone maybe further along, like at a PhD level, really wanting to dig into the nitty-gritty, what are the deeper areas of focus?
At that level, you're really working with the fields defined on the metric bundle, Y14 itself. Understanding the precise math of the pullback maps becomes critical. You're dealing with principal bundles built on top of other principal bundles on bundles. You need to master the structure and implications of the inhomogeneous gauge group, its specific right action on connections, and really get into the technical details of how the gauge incompatibility problem between gravity and gauge theory is supposedly resolved by the augmented torsion and the Shiab operator. That's where the really heavy lifting is.
This has been, well, truly illuminating. Seriously, I feel like I've at least glimpsed into this incredibly ambitious, maybe even revolutionary way of thinking about the fundamental structure of everything.
Well, you've definitely taken a whirlwind tour through a very intricate and forward-thinking theory. And frankly, you've followed along admirably. Hopefully for you listening too, you've gained some valuable insights into the sheer excitement and possibilities surrounding this quest for a truly unified description of physics.
Yeah, I think the core message that really sticks with me is that geometric unity proposes this fundamentally geometric origin for everything, all the forces, all the particles we observe.
Yeah.
It suggests that maybe all this complexity we see, it isn't fundamental complexity. Maybe it all stems from a deeper, simpler, more elegant, unified geometric structure underneath it all.
That's absolutely the key takeaway. And now, the really mind-bending part is to consider the implications.
Right,
If this geometric framework or something like it actually turns out to be successful,
right.
how would that fundamentally change our understanding of reality? The nature of space-time itself, the basic building blocks of the universe, what completely new avenues of research, maybe even technology, could it possibly unlock down the line?
Those are the big questions to chew on. And for you, our listener, if this deep dive into geometric unity has sparked your curiosity anywhere near as much as it has ours, well, this is really just scratching the surface.
Oh, absolutely.
We'd strongly encourage you to seek out more information. Maybe check out Kurt James discussions. Keep an eye out for any future talks or papers from Eric Weinstein himself.
Definitely worth exploring further if it's
Yeah.
caught your interest.
Because this quest, right, to understand the deepest secrets of the cosmos, it's just this incredible ongoing adventure.